I'm Anil Kumar, and in this video I'm going to discuss octic polynomials. Now, with the help of octic polynomials, I'll actually consider all the characteristics of the polynomials and generalize it for even degree polynomials. Octic really means degree 8, right? So in this case, octic polynomials means degree 8, right? Which is also even. And therefore, most of the characteristics which we discuss here will be applicable for all even degree polynomials. Let me use this space at the end to make some sketches of our polynomials. Last time in dealing with quintic polynomial, I kind of messed up on the sketches. They were too crowded. So I think this spread out will help us to understand the situation better. Now the parent octic polynomial will be kind of f of x equals to x to the power of 8, right? Well, when we say octic, we could have polynomials like let's say g of x equals to it could be like say x to the power of 4 times x minus 1, so 4 plus 1 5, and then we can have x plus 2, that is 6, and then we can have x minus 3 square, that makes it 8, right? So we could have the combination of factors so that the exponents add up to 8. So if that is the case, it is octic polynomial. Both these examples which I have taken, they have a leading coefficient as positive. So in this case, we know an is greater than 0. Leading coefficient is positive. So let me sketch the graph for these, and then we will discuss characteristics of octic polynomials where the leading coefficient is positive. Okay, so the very first one is x to the power of 8. It looks more like a parabola, but flatter and steeper, right? So it's kind of like this. Do you see that? So that is the kind of graph it is. As you can see, the graph has 1 0, right? So let's consider the number of zeros, possible number of zeros also as we move on, and we will also consider the end behavior. You see both sides are facing upwards, right? So that is how it is, and in this particular diagram there's 1 0, so we are just calling this as y, and this is x for us, and that is the origin. Let me also sketch this particular function, which is x to the power of 4, x minus 1, x plus 2, x minus 3 whole square. So I'm not really teaching you graphing skills here, but I'm kind of giving you that portion in short. So those of you who really want to understand details can follow the links. So we have a 0 here of order 4, which is at 0 itself. That's the first 0, and this is of order 4, right? So this is of, let me write, this is of order 4. We can read from here. The other ones are at 1. Let us say this is 1, right? Then we have 1 at minus 2. So this is 1 and this is minus 2. So we have 1 0 here, 1 0 here. And then we have 1 at 3. So this is 2 for us. And the other one is at 3, which is of order 2. Now since the degree is positive, end behavior is like both sides are upright. So end behavior is they are always facing the same ends. Now we can begin graphing. This 0 at minus 2 is linear, and therefore the graph will cross. Once you cross, you're on this side. Next 0 is at x equals to 0. It is of degree 4, which is even. So the graph is going to turn, right? So it's going to turn like a parabola, x-axis being a tangent. Then we have 1 which is at 1, linear 0, so it crosses like a straight line, and then at 3 it is again even, so it's going to bend like a parabola. Now connecting these zeros, we could sketch our graph, right? So let me just connect these zeros and make a sketch. So we'll start from here, for example. You can start from anywhere, right? So go like this. It bends, right? It bends and then it crosses. And now once it crosses, it has to bend, come to this 0 and then go upwards. Is it okay? And similarly, this also will move upwards. So you can see the end behavior clearly, correct? So what we have here in general, when the leading coefficient is greater than 0, that means when it is positive, in that case, the end behavior is that when x approaches negative infinity, y approaches, negative infinity, y approaches positive infinity, right? Going upwards. And when x approaches positive infinity, y also approaches positive infinity. Both, right? Upwards. So it is both are upwards. Important thing here is that right side is up. Right side is up, right? Right side up, and both on same sides. Both on same side. So that is characteristic for the polynomial even degree with positive leading coefficient, both on same side. Do you see that? So this is what I mean. Right up, this is right up. Is it okay? And both same side means both are up. So that gives you the kind of end behavior. Is that okay? Now, let's talk about zeros. Zeros, you have seen, we have at least one here in this case. So let me write one here. But what happens if I have a function which is like x to the power of 8 plus 1? If it is plus 1, this graph will move 1 unit upwards. Do you see that? Kind of like this. So there is no 0 now. So since we are moving from quadrant 2 to 1, we can move without crossing the line. That's the whole idea. So there could be no 0 at all. Therefore, the minimum number of 0 is always 0, correct? And maximum, of course, since the degree is 8, has to be 8, right? So it is 1, 2, 3, 4, 5, 6 till 8. Do you see that? Now that applies to any polynomial with even degree. So if n is even, in that case, the number of zeros is always from 0 to n. Do you understand? This is for even degree polynomials, right? Only, right? So we are considering also characteristics of even degree polynomials. For even degree polynomials, if leading coefficient is positive, right side is up and both are on the same side, and that is what the end behavior should be. Now let's talk about turning points. Now, since we are moving from quadrant 2 to quadrant 1, so if I like moving like this, I have to turn. So we have at least one turning point, at least one turning point. Do you see that? Now, if you turn once, you land up where you want to be. So there is at least one turning point. Now, take this case. If I turn once, I'm landing up where I want to be. But if I decide to make another turn, then I'm going to quadrant 4, where I don't want to be. So I have to make another turn. So you have to make set of 2 turns every time to ensure that you land up on the same side. And therefore, the number of turning points will be 1, 3, 5, and 7. 1 less than 8. Do you get the point, right? So maximum number of turning points will be for a quadratic function, for an octic function which has 8 zeros, right? So it will be kind of like this. Let's count. 1 turning point, right? 2, 3, 4. So 1, 2, 3, 4, 5. So we have 1, 2, 3, 4, 5, 6, 7, and 8. Do you see that? So number of turning points are 1, 2, 3, 4, 5, 6, 7. 1 less. And number of zeros maximum are 1, 2, 3, 4, 5, 6, 7, 8. That is the limit. Do you see that? So maximum you can have n minus 1. So for general cases, turning points could be from 1 to n minus 1. Do you get the idea, right? So 1 to n minus 1. That is the maximum turning point. Now in these graphs, you have seen that there is no restriction on domain. As far as I am concerned, all polynomials domain is always x belongs to real numbers. However, the range has the restriction, right? It turns. So it is y belongs to real numbers where y is greater than or equal to some absolute minimum. Correct? Now this turning point may lead to absolute minimum. So what you really notice is that if the degree is positive, in that case we are going to get absolute minimum, right? If the degree is odd, the range is all real numbers, we cannot have absolute maximum or minimum. This is very important to understand, and it's a very significant difference between even and odd degree polynomials, right? Now let me give you two more things here. One is even symmetry. Even degree polynomial may or may not have even symmetry. If I write a polynomial g of x as, let us say, x to the power of 6 plus x to the power of 8 plus x to the power of 4, all terms are with even degree, so that will be even symmetry. But if I introduce something which does not have even symmetry, then it will be neither. So for even symmetry, all terms should have even degree, right? We could also write a constant here. So even symmetry polynomials are all terms with even degree. Then the polynomial has even symmetry. If I introduce, for example, x here, it will be neither. That's very important to understand. Okay, now I've discussed everything about when the polynomial has leading coefficient greater than 0. If an, the leading coefficient, is less than 0, that means negative, then it moves from quadrant 3 to 4. Things reverse. It is like reflection on the x-axis. So all these things will reverse. So it will not end up in quadrant 1. It will end up in quadrant 4. It will not begin here. It will begin here in quadrant 3. So the behavior, especially the end behavior, will change, and in this case we'll have absolute maximum, right? So earlier we had absolute minimum. In this case we'll have absolute minimum. I will encourage you that take a few examples, just negative these, sketch them, and then see that these functions where the leading coefficient is less than 0 has end behavior from quadrant 3 to 4, and they may have absolute maximum, right? Not a minimum. So range will be less than or equal to that absolute maximum. But the number of turning points and zeros will remain what we have discussed here. Turning points will be from 1 to n minus 1, and the zeros will be from 0 to n. I hope that really helps. Thank you and all the best.